Hi everyone, my name is Arshdeep Singh. I'm a research fellow and a sustainability fellow in the University of Surrey, UK. So this work is a part of AFR Sound project sponsored by EPSRC grant, and this work is done with Professor Mark D. Plumbley. So topic of today's presentation is efficient similarity-based passive filter pruning for compressing CNNs. So the outline of today's presentation include introduction to CNNs and filter pruning. Then I will go with similarity-based passive filter pruning method, and then the proposed solution to make the similarity-based passive filter method efficient, and then in the end we'll see performance analysis, and we'll conclude the presentation. So CNN's convolution neural networks have shown promising performance for audio classification. However, CNNs require large number of parameters and they have high computations to achieve promising performances. And in the literature, it has been found that there exist redundant parameters in large-scale CNNs. For example, one of the studies shows that there are 73% of the filters which are not useful in contributing to the performance. And also, if we see we are looking to deploy CNNs on low source devices such as smartphones or Cortex M4 devices. So large scale CNNs, they are not useful, which actually works on software pretty well. Therefore, we are looking to compress CNNs to reduce their computational complexity and memory storage, right? One of the methods is to apply filter pruning, where few of the filters from the network are removed physically, and its corresponding feature map is also removed. Typically, the process in compressing CNN consists of obtaining the prune network after filter pruning. Then a fine-tuning process is performed to regain the lost performance, right? So one of the efficient methods which doesn't involve any data set in computing the filter importance, which filter to keep or which filter to retain, is the similarity-based filter pruning method, where from a set of filters in the filter space, closest filter pairs are identified by computing their similarity measures, which might be the cosine distance or any other measures. So generally they involves a similarity matrix S, which is computed for each of the pairs. Then one of the filters from the closest pairs is actually removed, and other filter is kept with an hypothesis that other filter is redundant. So the problem with this method is that this, since it involves the similarity matrix, and the computations in pairwise computation is of the order of n squared d, where n is the number of filter and d is the filter length, right? And this complexity is will be higher when there will be large number of filters in the network. So this is where we are contributing. So we aim to reduce the computation complexity in obtaining filter importance scores across various convolution layers in a passive manner without involving any data set. And we want to reduce the computations of in computing the similarity matrix, right? And we use the Nystrom approximation method for that, and we find that using only few columns of the similarity matrix, one can reduce the computation by 3 times without loss of any accuracy, right? Given, let's say, this is S, the similarity matrix of n cross n size, right? And then we are choosing only m columns, right? For example, let's take only the C matrix from out of this S matrix. Then we use this approximation, which is coming from the Nystrom method, and this approximation S is a parameterized by the number of columns and the K, which is the K rank approximation of this W matrix, right? This is where we are able to reduce the computations by choosing m, which is much lesser than n, right? And the experimental analysis we performed on 2 networks. One is the BGASH network, which is trained for acoustic scene classification, and another network which is DCASE network, which is again trained for acoustic scene classification but with complex data set. So what we found is that the approximation error, which is the S minus S square approximation, which is a function of m and k, find that choosing M, this diagram is shown for different networks, right? So for, let's say for this network, we find that choosing M, which is close to 9, right? And which means that choosing 9 columns out of these many columns across different layers, we can achieve this approximation error close to 0, right? So, and this same observation is also observed for other network as well, right? So choosing small number of M, one can compute the similarity matrix which has approximation error close to 0, right? And then we experimented with K, right, by varying K at fixed number of M. So we find that typically M is equal to K is giving the approximation error close to 0, right, once we obtain M, right, given M, right? And by choosing the few columns from the similarity matrix, right, and then approximating it, so we can reduce the pruning time to compute the importance of filter across different layers by approximately 3 times, right? So this time, so this is red here shows the original time, right, for C3 convolution layer. Then we have reduced to this much, right? And this is time which is shown for other network, right? So if we see the results, and here we show a table for network 1 and network 2, right? And no pruning baseline means that this is the performance with respect to the unpruned network, right? And we find that if we see this pruning time compared to similarity based method, that is approximately 3 times less than that of the similarity based methods. And if we compare the performance of the similarity based methods with the active pruning method, which actually use data set for pruning, the performance is still can be achieved more, and there should be more robust methods which can achieve similar performance. So that will be our future scope to improve the performance of this particular passive filter pruning method, which is efficient, yes, that we have proposed, but performance wise we need to improve a lot. But if we see the resources like filter storage or feature map storage when we perform pruning, so our method has advantage over the active pruning methods. So we propose a passive filter pruning method where we remove filters with pairwise similarity measures, and we reduce the computation complexity in obtaining this complex similarity based method, right? Thank you very much.